Okay. So I know it's not quite time yet, but who's in Babson's class? Okay. So FYI, you guys are kind of covering what I would classify as the material from the syllabus pre 2020, aka the way the class used to be taught. And the current syllabus specifically doesn't cover all this work stuff you've all talked about in class, I assume, and the moments, which you're about to cover, I think, tomorrow, maybe. That said, you get to learn it, and we will cover it. But for those of you not in Dobson's class, today will probably not be particularly applicable to anything you're doing in your class. I should say not completely not applicable, just we're going to learn about work and fluid force and moments on Thursday, probably. And while that is stuff, certainly moments will come back in 21D, which is where you should learn about moments when you have double and triple integrals because it's much better. You don't have these janky formulas with weird stuff. You have nice formulas with much better with a double integral. But the work stuff is, I mean, it's kind of useful. It's interesting to see how you set things up and how we still think about integration, but you will not be covering that material if you're in Parallax class. So just so you know. Yeah. Co-21B. Today is something, the 13th. And I should probably look at my notes. Yeah, my notes. Let's make it bigger. Let's do that. Let's do that. So we'll try to get through all the work stuff today, but there are a lot of different types of ways of thinking about work. I suppose I should start off by talking about like what is work. So let's see. Is it time? It's time. Sure, let's get going. So work is equal to force times distance, or we sometimes say distance against that force. A couple examples that are easy. Example, a 5-pound book is lifted a distance of 4 feet, say from the floor to a table. How much work was done? Well, the work done is the force, pounds is a measure of force, times the distance that force traveled against gravity, 4 feet. And if we multiply those things together, we get 20, and the units are really lovely, foot-pounds of work was done. Love that American system of units. Really, really good. Yeah, I know. So the metric system has much nicer names for things. Or another example. So in the US system, force or weight is measured in pounds. In the metric system, force or weight is measured in newtons. It's kilograms times 1 meter per second squared. So in a metric system example, a 100 Newton chair is lifted 2 meters, which is pretty high for someone like me. The work done is, again, easy. It's 100 newtons of force multiplied by 2 meters of distance, which is going to be 200 Newton meters, also known as 200 joules. So 1 Newton meter is 1 joule in the metric system. That's the unit we typically like to use. We're talking about work in the metric system. So those are very straightforward examples where you have a constant force moved some distance. But of course, we're going to make it harder because we're going to have forces that are not constant. And the typical place we start is with springs. Let's start with springs. So if you've ever stretched a spring, you might notice, and again, this a spring with like some tension to it, not like a slinky. A slinky is not a good example of a spring because it doesn't have a lot of tension. But like if you've ever stretched a spring, it gets harder to stretch out the further you stretch it, or compressing it the same. It gets harder to compress it if you've gotten to a point where like it's providing more resistance. So the further a string is stretched, or compressed from its natural length, you're going to have to increase how much force you're using to continue stretching or compressing it. Or in other words, we have the following. Let's make sure I use the right words here. The force required to stretch or compress, we usually talk about stretching, a spring is approximately, and for us, we'll just say it is, proportional to the amount it is stretched by. This is what's called Hooke's law. So we have that the amount of force is equal to some constant times x, where k is just a constant and the units are not worth mentioning, and x is the distance stretched from its natural length. So let's look at some examples. And there's a couple of different ways of phrasing these questions, which we'll get into here. And please do, well, I should say, please don't stop me if you have questions about the physics part of it, because I'm not great with the physics part, but the math part I can certainly talk about. The physics, sometimes I'm a little shaky on, I will not lie. So let's look at this first example. If 20 newtons of force is needed to sorry, I'm looking at this. Yeah, I'm going to write this slightly different. To hold a spring stretched from its natural length of 5 meters to a length of 7 meters. And yes, there are really big springs out there in the world. What is the spring constant K? Well, that's a relatively easy question to answer. Our force should equal K times X. So that's going to tell us that our force of 20 newtons is equal to K times, we stretch this a distance of 2 meters, 7 meters minus 5 meters. So that's going to be K equal to 20 divided by 2, which is 10. And no, I don't care that it's newtons per meters, but I guess I'll write it anyway. That's not the interesting question. The more interesting question is, sure that's A, I guess. The more interesting question we can ask is, how much work was done to stretch the spring from its length of 5 meters to 7 meters? So the problem here is we can't just multiply the numbers together. We can't multiply the force of 20 newtons by the length of 2 meters because, well, every time you stretch the spring further out, the amount you stretch it by is now longer, so it's going to take more force each time. So here's how we're going to think of it. And again, this is where I need to be extra careful here. So let's say we have the spring that looks like this. And here is the spring sitting in its natural length of 5 meters. And then we're going to stretch it further to a length of 7 meters. So this length here is 2 meters. And the idea is we're going to look at a small little increment of the spring, which has some length dx, not surprisingly. And we're going to say, for that small length of spring, we're going to ask how much work we have to do. Sorry, I'm going to make sure I'm going to say this exactly the right way. So, sorry, this is where I think of it one way and other people think of it a different way. We're going to think of how much work is done stretching the spring from here to there. So for that short little distance, we can imagine that the force is essentially constant. So what's going to happen here is we can say that the work done to stretch the spring from this length here of x. Oh, I did the thing I didn't want to do. Sorry, ignore that x. Apologies. X is not the total length, it's the length beyond its natural length. So from this length x to x plus a little bit more, x plus dx is going to be, well, work is force times distance. The force is going to say essentially constant because this spring is stretched to essentially a length of x beyond its natural length, right? Because x and x plus dx are pretty much the same. So we're going to say that the force here is going to be, well, we're going to use Hooke's law and say the force is 10 times x times the distance we're stretching it or moving it, which is dx. So again, force times distance. So that's how much work it takes to move the spring from x to x plus dx. But we want to add up all those little stretches from 0 to 0 plus dx, from dx to dx plus 2dx, from 2dx, right, all the way from 0 to 2. So the work for this little strip is that much. The total work is going to be, well, just like every other time we've drawn a little slice and then wanted to add it all up, we're going to integrate. The total work is going to be the integral from 0 to 2 of 10x times dx, which is not terrible to calculate, right? The integral is easy itself. That's just going to be 10x squared over 2 from 0 to 2, which is 5 times 2 squared minus 0, which is 20. 20 joules. Question?
Why dx and x are just like those little pieces?
So I wouldn't say x is a little piece. So I would say that, let me draw the picture again, because I will admit my picture is not the best. So the idea here is, here's the spring sitting at its natural length of 5 meters. And then we've stretched it some amount, say x, which is not a tiny amount, right? X is anything between 0 and 2 meters. And we're saying if it's sitting at stretched x beyond 5, and then we're going to stretch it just a tiny, tiny bit more to x plus dx. Well, to hold the amount of force required to hold the spring stretched at x is k times x. So to hold the spring at x meters beyond 5 meters, we require k times x newtons of force. Bless you. And then that's the amount of force we're exerting on the spring, and then we move it just a little bit more. So the amount of force really didn't change, right? It's just a tiny smidge more, but we moved it that tiny smidge of distance. So the work done to move it from using this much force at this point to this much force, tiny, tiny, tiny bit more force at this point, is going to be, the work is that force, k times x, times the small amount of distance we just traveled. Now, as we go along here, sometimes the small amount we move is going to be a small amount of distance. Sometimes the small amount we change is going to be a small amount of force. And it kind of just depends on which way it's easier to think of it. And it does get a little confusing sometimes. Also, here's the attendance sheet. And also, my feelings won't be hurt if you're in part of this class and you don't want to stay for this. So I will understand if you have a desire to leave and if you're not learning the stuff in your own class. But you can also stay because it's kind of neat. So for this one here, to stretch it from its natural length of 5 to a longer length of 7, it took 20 joules of work. How much work is it going to take to stretch it even further from a length of 7 meters to a length of 9 meters? So how much work to stretch the spring from 7 meters to 9 meters? It should not be the same amount of work, even though we're stretching it the same length. But the thing is, it takes much more force to hold it at 7 meters than it did at 5. So it's going to take a lot more work to go from 7 to 9 than it was from 5 to 7. The calculation is still very much the same. It's going to be the integral, but now instead of from 0 to 2, we're going to go from 2 to 4 because we're stretching it from a beginning length of 2 meters beyond its original length to an ending length of 4 meters beyond its original length. It's still the same integrand. It's still the integral of our force times our distance. So when we calculate that, we're still going to get 5x squared as the integral. Evaluated from 2 to 4, we're going to get 5 times 4 squared minus 5 times 2 squared, which is going to be 5 times 16 minus 5 times 4, so 5 times 12, which is 60 joules. So 3 times as much work as it took to stretch it from 0 to 2, from 5 to 7 as it did from 7 to 9. So springs are usually not too terrible. The thing to remember with springs is the limits of integration have to be not the lengths you're starting with, but the amount of difference in the length from the spring's length to its original length. So if we just ask one more question, in fact, I want to be able to set this next one up. So I'm going to ask you all to set up an integral for the amount of work to stretch a spring with a natural length of, I don't know, sure, let's not be confusing, of 2 meters from a length of 3.2 meters to 4.6 meters with a spring constant of K equal to 5. I'll remind you that force for a spring is K times X, and work is going to be the integral of your force times your dx. So when I do a problem like this, I like to draw my picture like this. My spring, and then I have its natural length here, 2 meters, which I like to think of as x being 0, because my natural length is a stretch of 0 meters. And then I'm stretching it from a length of 3.2 meters to a length of 4.6 meters. So at 3.2 meters, I'm 1.2 meters stretched beyond its natural length. And at 4.6, I'm 2.6 beyond. For these problems, your units should always be meters. So if they give you lengths in centimeters, you have to change that to meters. So in this case, my work should end up being the integral from 1.2 to 2.6 of 5x dx, which I know you all could calculate. Okay, so springs, not too terrible. The only thing I'll say to be careful about is if you're finding the spring constant, there's two different ways they can phrase the question. They can phrase the question as it takes this much force to hold the spring at a certain length. And then you can just say, okay, force equals k times x, find k by dividing. They might also phrase it as it takes this amount of work to stretch the spring from its place to a place. And then you have to set up the integral and solve for k. Let me show you what I mean. I feel like just saying that's not enough. So let's do the following problem. So yeah, let's say I'm going to make up some terrible numbers here. 40 joules of work are needed to stretch a spring from its natural length of 110 centimeters to a length of 130 centimeters. What is our spring constant K? The answer isn't going to be found by taking 40 equal to K times X and dividing by whatever the length is. Because that equation, this equation, F equals K times X, that's a force in newtons, not an amount of work in joules. So here, if we're given 40 joules of work, we're being told what the integral is. So we're being told that if we stretch this spring from its natural length of 1.1 meters to a further length of 1.3 meters, where x is equal to 0.2, that amount of work it took to stretch from there to there is 40 joules. So that means that the integral of kx dx from 0 to 0.2, that should equal 40. But then we actually have to do the integration to solve for k. So be careful how you read these questions. The words are meaningful. In this case, it's still not terrible to do, except for the decimals there. So this equation, I should leave myself some more room here. We're going to end up having that kx squared over 2 from 0 to 0.2 is equal to 40. So that's going to become k times 0.2 squared over 2 minus k times 0 equals 40. So k is equal to 40 times 2 divided by 0.2 squared is 0.2 times 0.2, which is 0.04. 40 divided by 0.04 is 4,000 divided by 4, so 1,000. That's going to be 2,000. That's our K. So they tell you how much work is done. You have to have the integral to find K. They tell you how much force is required to hold it at a certain length. No integral. You're just setting the force equal to K times X and solving for K. But enough about springs. There's so much else to talk about. So when we're talking about work, the idea is always force times distance. And in my mind, I'm always thinking of force as weight. To me, force is weight. That's just how I think of it. It's not always the right way to think of it, but it's almost always the right way to think of it. So let's look at this next situation here. Yeah, okay. And we're going to talk about this one in two different ways because, yeah. So let's look at the next one. I guess this is two. There probably some twos before, but okay. A 50-foot cable weighing, sure, 150 pounds. It's a heavy cable. Is used to pull up an elevator weighing 1,000 pounds. How much work is done when both the cable and the elevator are pulled the entire 50 feet? And in my opinion, there's two good ways of thinking about this. I'm going to kind of show you the way that I don't usually think about it first, because lots of people prefer to do it this way. I'm not one of them, but that's okay. Doesn't always have to be my way. So here's my elevator down here with a force of 1,000 pounds. And we're going to label this again. I think this is kind of weird, but we're going to say the top here is x equals 0, a distance of 0 from the top. And down here, x equals 50, a distance of 50 feet from the top. And then, well, let's talk about the elevator first. The elevator is the easy part. The elevator is a constant force of 1,000 pounds, and it's going to move 50 feet. So the work done for the elevator requires no integral. It's just going to equal our 50-pound force multiplied by our 1,000-pound force, excuse me, multiplied by our 50-foot distance to get a work of 50,000 foot-pounds. My favorite unit ever, foot-pounds. On the other hand, the cable is different because the entire length of cable, the entire 150 pounds of cable, not all of it's going to travel 50 feet. In fact, only the very end of it's going to travel 50 feet. Lots of other parts of it travel different distances. So we're going to do this way the first way, even though I don't love it. So here's how we're going to think of this. We're going to take a little smidgen here, a little dx, and we're going to call this distance x. And here's why I have to read this because this is not the way I think about it. So here's the way you can think about it this way. The cable gets lighter or less heavy as it shortens. Okay, I buy that. So the force changes, or the weight of the cable changes as we start reeling it in. And for something that's variable, we need to use an integral. So here's how we're going to think of it. And again, yeah. So I hate doing it this way. I'm not going to lie, I really hate it. So when there's X feet of cable out, with X feet of cable, the work required to move it dx feet is, well, again, work times distance. Sorry, force times distance, force times distance, force times distance. So it's going to be, well, and yeah, this is kind of smart. It's going to be some multiple of x times dx. Why did I use a k there? To kind of harken back to the spring thing, even though it's not quite the same. There's our force, there's our distance. The weight of that x length of cable, well, it's proportional, right? The total cable is, I mean, we should just find like the weight of the cable per foot. So if the total cable weighs 150 pounds, we can say that 150 pounds divided by 50 feet, the cable weighs 3 pounds per foot. So if it's X feet long, it's going to weigh 3 times X pounds. And then we're going to integrate. So the total work is going to be the integral. Well, my lengths of cable can be as short as 0 to as long as 50. So I'm going to integrate from 0 to 50, 3x dx, which is going to be 3x squared over 2 from 0 to 50, which is going to be 3 times 2500 over 2 minus 0, which is going to be 3750 foot-pounds. And then we add it all together. So the total work is going to be 50,000 plus 33,007. Oh my gosh, 50,000 plus 3,750, which is 53,750 foot-pounds. And even though I don't care to do it this way, it often is the better way to think of it because it's a little more applicable in various strange situations, especially like when you don't pull it up the entire way. It's often easier to think of it this way than the other way I like to think of it. So if it were me, I would have thought of it as instead of a force of or a weight of 3 times x amount of cable moving a distance of dx, I would have thought of it as a force slash weight of 3 times dx, this little bit here moving a distance of x feet. You still get the same result. You still get 3x times dx. But to me, it just feels, I don't know, it just seems to make way more sense to me in my brain to think of it as this small amount of weight of cable moving that distance. And then this little small amount here moving that distance. And then each of the small amounts move a different length from anywhere from 0 to 50. But even though I like that better, and I think it's easier to understand, I do think doing it this way is an approach that offers you more kind of genericness. Like it's easier to apply it to other situations. Because sometimes they'll say something like, how much work is done if the elevator only goes like halfway up? And then it can be challenging to do it the way I like to think of it. So even though I said I was going to do it the other way, I'm not going to do it the other way because I think, even though I hate it, it's better for you all to do it this way. So try to think of it this way. Try to think of it as not what I just said, but as this weight of cable moving a small dx length or distance. It can be challenging, maybe more so for me than for any of you. Hopefully, it's not challenging for you. All right, let's see. Yeah, we can do that. All right. Well, yeah, we should do one of those. Okay, so we'll do one more like this, and then we'll talk about some other kinds of work. There's lots of kinds of work. What time is it? Okay, we got time. Sure. So one more of these, which is kind of your classic terrible problem, a leaky bucket problem. So here is a leaky bucket problem. A leaky bucket weighing 5 pounds, the bucket itself weighs 5 pounds, is pulled up 20 feet by a uniform rope, by a uniform density rope, weighing, or I should say with density, 0.25 pounds per foot. The bucket is initially full of water. And that has a weight of 16 pounds. And here's why I really hate this problem. Well, actually, not really, but because it just feels like a dumb problem. And as you pull it up, it finishes draining right as it reaches the top. So why would you do it? Maybe you didn't know it was leaky, but otherwise it seems like kind of pointless. Unless you're trying to get a workout, I guess. So how much work was done lifting the whole shebang? The bucket, the rope, and the water. Well, the first two parts, the bucket and the rope, are just the same as the elevator and the cable. Same idea. So if we draw a little picture here, our leaky bucket. And this is a distance of, yeah. This is x equals 0. Down here is x equals 20. So let's talk about the bucket first. So the work for the bucket is easy. The work for the bucket is just the weight of the bucket, or I should say the force of the bucket, 5 pounds, times the distance the bucket's going to travel, which is 20 feet. So a nice even 100 foot-pounds of work. The rope, and I'll test out my own ability to think of this the right way. So we're going to say that this X length of rope, which has a weight. So the X length of rope has a weight of X times 0.25 pounds per foot. So that is the weight or the force of X feet of rope, or the weight of X feet of rope. And it's going to move a very, very short distance of dx. All right, I think my brain can make that work. And then, but that's just how much work is done when we move from there to there. We want the whole thing to move, so we're going to add up all the works done by all the whatever lengths of rope, each moving their own little dx. So the total work is going to be for the rope, the integral from 0 to 20 of 0.25 times x, or as I would probably prefer to write, 1/4 times x. Again, that's not terrible. It's going to be 1/4 times x squared over 2 from 0 to 20. That's going to be 20 squared, so 400 divided by 8, which is 50. 50 foot-pounds. Do make sure you're convincing yourself that I'm only plugging in the 20 and not worrying about the 0, because when I plug in 0, I get 0. Right, we definitely are checking for that. Okay, so now for the water. So how much water do we have at each height? Well, this part is always the part that feels kind of weird, but it's actually not that terrible. So yeah, what I would say here is we know that at x equal to 20 feet, the amount of water, or the weight of the water, is going to be 16 pounds. And I probably could have included some words here that would have made this, yeah, there's something I should say, which is usually assumed, but I will say it. And we know that x equal to 0 feet, the weight of the water is 0 pounds. And we assume, or it's usually said, that the water drains out like at a constant rate, meaning there's a linear relationship between the height of the bucket and the weight of the water. So what that means is you can essentially write an equation for the weight of the water as a function of x just by doing like a line, right? So we know that essentially the slope of our line, well, it's the change in the y over the change in the x, or it's the change in the output over the change in the input. So it's going to be 0 minus 16. I don't know why I did it that way, but I did. Over 0 minus 20. Still works. You can subtract either order. It's still fine. That's going to be 16 over 20, which reduces to 4 over 5. So my slope is 4 over 5. And oh, this is the easier way of doing it. Okay. I usually do this a different way, which the math is a little harder. So there are merits to doing it this way I don't like. So the weight of my bucket is 4/5 whatever the value of x is. Let's check that out. If x is 20, yeah, my bucket weighs 20 times 4/5, which is 16. And if x is 0, my bucket weighs 0. If x is 10, my bucket weighs 8. Okay, that seems reasonable. 8 pounds. So then the idea is, and this is where I will kind of go back to the way I like to think of it, that constant force, so that, right, so if we move like the bucket from like say here to, up here, well then the weight of the water in the bucket isn't changing really at all, and it's moving a distance of dx. So the work exerted is going to be that weight force times the distance traveled, dx. So the work here is going to be 4/5 x, our force, times our distance, dx, and then we're going to integrate that as well from 0 to 20. Let's look at one thing here. Where'd you go? Sorry, I lost the thing I was doing. Sure. Okay, so that's going to be same sort of deal. 4/5 times x squared over 2 from 0 to 20. So we're going to get 4/5 of 400 over 2. That's going to be 160 foot-pounds of work. So putting it all together, 160 plus 50 plus 100, we get a total of 310 foot-pounds to get no water. So these are pretty typical examples, and these are definitely similar to the problems that are in the textbook that Babson has assigned. Before I continue on, questions about any of the things that I know there's a lot of questions you could ask, but are there any specific things I can address, make more clear? Maybe. Yeah. Hmm. So I'm just checking something to make sure that my thought process is not crazy here. Did I change the number? Let me check one thing here. Sorry, I feel like I'm losing my mind here. I made a mistake. That's terrible. I was trying to do it the better way, and now I'm seeing something that's making me think I've done it incorrectly. That's a bummer. Oh, wait. No, I think I see. I think, sorry. Yeah, I think whoever set this problem up. Sorry, I'm looking at the solution someone else wrote to this, and I think the way they set up their line is incorrect here. I'm gonna go with this for now. I'm pretty confident it's correct. I don't wanna try to fix it just to lead you astray. So I'm gonna think about this on my own later. And if I turn out to have done something wrong, I will correct it and let you all know. But for now, we'll pretend like it's right. I think it's right. I just don't want to spend any more time thinking about it when we have so many other things to talk about. So the other sort of things we often talk about with work are the work done pumping water from one elevation to another. Let's look at some examples here. Where'd you go? Examples. Yes. So here's unfortunately, not a typical example. So let's look at the following. A cylindrical tank is half full of water. How much work is done pumping it all out, or all to the top, I should say. And we might need to know a few things about like how tall this. So let's draw our cylinder here, and I'll give you all the important details as we draw it. The height of my cylinder is 10 meters. The radius of my cylinder is 2 meters. Yes. Of course. Yes. Sorry about that. You can just yell at me. You say, hey, James, we can't see. It's really okay. I won't be offended. And this tank is half full. So we want to figure out how much work is required to move all of this water out to a height that's the very top of the cylinder. So usually when I set these up, yeah, I prefer to set them up kind of not how I'd done the previous two problems. I like my bottom to be zero and my top to be the height, as opposed to the top being zero and the bottom being how far it is. Either way can work, you just have to be careful about it. So we're going to say that this bottom part here, this is a height of y equal to 0 meters, or you can use x, but we tend to use y. And this top is a height of 10 meters. We need to know a few other things. We need to know, first of all, the density of water. And we typically assume that the density of water is equal to 1,000 kilograms per cubic meter. We're also going to know what gravity is doing for us. Gravity is 9.8 meters per second squared. But that's kind of, whatever. So then the density of water is going to be that times that, which is going to be 9,800 newtons per cubic meter. This is the mass density. This is the weight density. But that's not really the hard part. The hard part is setting this whole thing up. So again, work is force, weight, times distance. So when you're trying to figure out how to set a thing up, you essentially want one of those things to be constant based on your slice or the little snippet you're taking. So here, we're going to look at a slice or a slab of water that all has to travel essentially the same amount of distance. So we're going to go down here, say, cool, this amount of water here, which I've dyed red, this amount of water here, that slice of water, well, we're going to imagine that slice of water is at a height of y and has a distance of 10 minus y to travel. And yeah, I just think that's the better way to do it personally. So cool. The force, sorry, apologies, the work to move that slice is going to be the force, aka the weight of that water, times the distance it has to travel. Force of that water is just the volume of water multiplied by its density. So that's going to equal the volume of the water times the density of the water times the distance it's going to travel, which we just said was 10 minus y. The volume of the water, well, the thickness of my slice is dy, and the area of that shape is a circle. It's going to be pi times 2 squared. So the volume of my water is going to be pi times the radius squared times dy times the density of the water to get the force is going to be 9,800 newtons per cubic meter times 10 minus y. And kind of the gnarly part here is that most of this stuff in here is all just constants that are going to come out from the integral. So if we're going to try and find the total work, we're going to add up all the work done for each slice of water at each different depth. So it's going to be the integral of, I'm going to pull out in front of my integral the 4, the pi, and the 9,800. Maybe, yeah. All of that comes out in front, and I'm left with 10 minus y dy. And here's a question that might be a little less easy to answer. What are my limits of integration? I'm happy to clarify. My lower limit of integration, well, so how low do my slices go? To y equals 0. How high do my slices go? To y equals 5. Because, right, this tank isn't full of water. This tank is half full of water. So our highest slice is 5 meters above the bottom. And often the limits of integration for these problems are challenging sometimes. So then the rest of this is not terrible. I mean, relatively not terrible. We've got 4 pi times 9,800. And then we're integrating 10 minus y. So we're going to get 10y minus y squared over 2. Evaluated from 0 to 5. That's going to end up being something terrible. 4 pi times 9800 times 50 minus 25 over 2 minus 0 minus 0. And that ends up being a gross number. 101,470,000 joules. Or 9,800 times 4 times 37.5 times pi. Oh, pi, don't forget the pi. Never forget the pi. So this one is in my opinion, oh, I should plug in my computer before it turns off. Good idea. So this one's kind of the easiest version of this type of problem because we didn't have a slice whose volume was changing as we went up or down. So let's look at another example of one of these work done pumping water questions. The idea is going to be very much the same though. So let's say we have, yeah, let's look at this situation. So now we're going to find, instead of writing all the words, let me just say the situation. So we have a, what is it? A hemisphere whose radius is 6 feet and is filled to a depth of 4 feet. How much work is required? Bless you. How much work is required? I'm going to make this one a little bit more interesting to pump all the water out of a spigot that empties 3 feet above the top of the hemisphere. I will say for these problems, drawing a picture is kind of vital. So let's look at our situation here. I've got that's probably not the best way to draw that, James. Fine, we'll do it like this. Wow. There's my hemisphere drawn in the wonkiest way possible, maybe. Sorry about that. I'm gonna draw it again. And we have a spigot coming out of the top. And so just for the sake of everything here, we have that this distance is 6 feet. This distance is another 3 feet. So how are we going to set this thing up? Well, first of all, we don't really need the 3D picture here. Yeah, it's kind of good to think about how we're going to have a slice of water that is, a disk. Gosh, my pictures are getting worse by the moment. But let's draw this in a more two-dimensional way. Okay. So, and my water is only filled to a depth of 4 feet. So, there's my water. So how am I going to set this up? Well, I would probably choose to set it up in the same sort of way. I'm going to call the bottom y equal to 0. This is y equal to 6. This height is y equal to 9. I need to think about my slice of water. So here's my disk that's up my slice, which I'm going to represent as a horizontal kind of rectangle over here, even though that's really my disk of water. And that disk of water is at a height of y. Oh, and I forgot to say one thing, sorry. The weight density of water in the US system, the density of water is 62.5 pounds per cubic foot. It might be 62.4 or 62.5, depending on how hot things are, but We're going to go with 62.5 because the math is a little nicer with that one. All right. So same idea. I need to find out the work that's done for my slice by saying it's going to be my force times the distance it travels, which is going to be the volume of water times the density of water. That's my force. And the distance traveled is going to be, well, if it's at a height of y, it's going to travel a distance of 9 minus y to get all the way out of the spigot that's 3 feet above the thing that has a radius of 6 feet. The volume of this slice is more challenging because the radius of that disc is not the same, right? It's not a cylinder. So to find this radius here, I really need to draw something. I need to draw that hemisphere radius, which has a length of 6. And I need to draw this length here. So that's 6. This length is 6 minus y, and this length is my radius. So let me draw that triangle so everyone can see it a little bit better. So there are the 3 sides of my right triangle. And I want to know what the radius is based in terms of y. So we're going to say that r squared plus 6 minus y squared equals 6 squared. And then we're going to solve for, well, we're going to be smart. Check this out. We don't have to solve for r. We're not going to get a square root. You know why? Because when I write this equation here, my volume is going to be the area of this circle, which is pi times whatever that r squared is, times my thickness, which is my dy, times my density, which is my 62.5, times my 9 minus y. Okay, but now if I solve this for r squared, I get r squared equal to 36 minus 6 minus y squared. If we multiply that out, that's 36 minus 36 minus 12y plus y squared. And then if we subtract, the 36's cancel, and you get 12y minus y squared. So it kind of works out a little bit more nicely. It could have been worse, which I guess is always true in this class. It always feels like it could be worse. Although this is kind of the worst. I won't lie. These problems are kind of terrible. But let's go ahead and finish this off. So the work for our slice here is going to be pi times 12y minus y squared times dy times 62.5 times 9 minus y. So then the total work done is going to be the integral. Okay. The picture's still there, although I didn't actually draw the fact that this was at a height of 4 feet. So my slices go as low as 0 to as high as 4, because that's the depth that the hemispherical tub was filled to. And then we have all this. So pi times 12y minus y squared times 62.5 times 9 minus y dy. And then to make this look less terrible, we pull out the 62.5 of the pi. And then the 12y minus y squared times 9 minus y, we would have to multiply out. Which again, in the world of integration is not that bad, right? It's just a polynomial. It's not the best ever, but it could be worse. Which I guess is the refrain for today. So 12y times 9 is 108y. 12y times minus y is minus 12y squared. Minus y squared times 9 is minus 9y squared. Minus y squared times y is plus y cubed. And then we'd integrate and get 62.5 times pi times, yeah, I know, 54y squared minus 12 minus 9 is minus 21 y cubed over 3 plus y to the 4th over 4 from 0 to 4. And then might as well do one more step. You're going to get 54 times 4 squared minus 7 times 4 cubed plus 4 to the 4th over 4. At least the numbers are not too terrible at that point. It will simplify it. We don't need to go any further though. So for many of these problems, you might just get asked to set it up. Because obviously, doing the integral here is not showing that you know anything new, right? We know how to multiply things out and integrate polynomials. So I would be willing to bet that if someone's going to ask you a question like this, they're going to ask you just to set it up because the setting up part is the hard part. And the integration part, while gross, is not hard. It's just keeping track of everything carefully. So that's what I would kind of hope for. All right, let's see here. Work, work, work. Yeah. Yeah. Oh, so we needed this triangle so that we could find the volume of this slice of water. So that slice of water, right, the lower that slice is or the higher that slice is, the bigger or smaller it's going to be. And so this triangle is this triangle here. And the bottom side of that triangle is the radius of our slice of water. So then the volume of that slice of water is the area of the circle, pi times r squared, times the thickness of the slice, which is dy. And that r there is that r there that we then found in terms of y. Because if we're integrating this in terms of y, every variable has to be in terms of y. So I would say sometimes experience is the answer, but I would point out, so when I drew this here, and again, my first picture was not wonderful. We had this, water at a height of 4, and then we had a slice here. And that slice, well, it's a disk. And if I'm trying to find, right, if I'm thinking of that disk as, a shape like this, I need to know what its radius is. I need to know how long this section is right here. And the problem is the only thing I really know about this bowl is it's a hemisphere with a radius of 6. So typically when you're doing problems like this, and this is probably true in 21A as well, when you're trying to like optimize things, if you're trying to like somehow get an equation to rewrite your variable in another way, you often draw the line or the segment that connects the center of your object to where the thing you're trying to deal with touches the thing you have. It's not like a great way of saying it, but it's often true. Like if you ever did a problem where like you're trying to maximize the volume of a cylinder inscribed in a sphere, you do the same sort of thing. To write the equation of the cylinder with only one variable, you need to have a way of relating the sphere's radius to the cylinder's dimensions and drawing that line from the center of your thing to the place where the things touch each other almost always gets you what you need. I know it sounds kind of silly to say it that way, but it is true. Because then I can say, oh yeah, I do have a right triangle here. And I know that if this strip is at a depth of y feet above the bottom, and we know that the radius of my sphere or hemisphere is 6, so this length has to be 6, this whole length here, then for my triangle, well, we know that this length here, the hypotenuse of my triangle, is the radius of the hemisphere. This length here is the length we're trying to find, the radius of our disk. And this height here, well, if the strip is at a height of y off the bottom, it's still got 6 minus y more to go to get to the top. So that length is 6 minus y. And that allows us to find a way of writing r in terms of y, which we needed to do since we knew we were integrating with respect to y because we had a dy. Fair question. It's always kind of a challenge to figure out how we write the volume of our slice or a strip or whatever we've got in terms of the variable we need. It's kind of been the problem with every problem we've done today. The leaky bucket problem also had that same thing going on where we had to figure out how to write our volume of water in terms of the variable we're actually integrating with respect to. I need to look back at that problem again. But make sure that one's right, or if it's not, tell you what it should be. So yeah, let's see. Is this problem worth looking at? No, I don't think so. Okay, so how much time? No, we should do one of those. So the last kind of the other kind of topic after work is the fluid force on a submerged thing. So yeah, we have enough time. There are more work examples. Obviously, hopefully you're all aware of Grant's website. You should look at Grant's. Grant has some good examples, many of which I've used today, but not all of them. So let's look at the following situation. This is fluid force. So we're not calculating work anymore, we're calculating force due to pressure. So let's say we have an aquarium. An aquarium with dimensions 7 feet by 2 feet deep by 4 feet tall is full of water. Again, water having a density of 62.5 pounds per cubic foot. So we want to know how much force is being exerted on the bottom of the tank. Let's draw a picture. So here's our tank. It's 7 feet wide by 2 feet deep by 4 feet high. And I would point out that I've lost my place. Where'd you go? Yeah, I guess it's there. So the idea is that the force that's acting on a little square at the bottom is just the amount, I should say, is the weight of water that is above it. So we can think of like this little square of water or square of bottom of my tank. There's this whole column of water sitting directly above it. And all of that weight of that water is pressing down on the bottom of the tank. So the easy calculation here is not too terrible because we can say that and again, sorry, I should ask the question here. We want to find the fluid force on the bottom of the tank. And I feel like I've forgotten to say something, but we'll come back around and say it. So we should point out here that every point on the bottom of the tank is at a depth of 4 feet. So we can calculate the fluid force as being equal to the density of the water times the depth of the water times the area that we are exerting that force onto, which in this case is going to be 62.5 times a depth of 4 feet times an area of 14 feet squared. And I guess I could have put pounds per cubic foot here. The only reason I'm putting the units in there is just so we can see that the feet are going to cancel and we're going to be left with just pounds, which is a measure of force. So we are feeling good about that. And then we get some terrible numbers. I will mention one reason I like 62.5, and it might not be the right number, but fine. Because 62.5 times 2 is 125. 125 times 2 is 250. So when you multiply it by just a couple even numbers, it gets much nicer. So 662.5 times 4 is 250 times 14 is going to be 2,500 plus another 1,000 is going to be 3,500 pounds of force being exerted on the bottom of this thing. And I need to look at one thing. Sorry, I just want to double check something before I get carried away here. I know it's not the most exciting material, but it is stuff we're talking about. Where'd you go here? There we go. Sorry. Okay, that's it. Yeah. So that's the general idea, is the fluid force due to pressure is just the area times the depth times the density of whatever the liquid is that's on top of it. Which oftentimes we make up liquids and just say, here's a pretend liquid with a density that's really nice. So the multiplication is not terrible. Now, it's all nice and easy when everything's at the bottom. But the thing is, there's also fluid force due to pressure on the sides, on the glass that's on the sides as well as on the bottom. And and again, the physics here is not my forte, but it is true. Like it doesn't matter if it's directly above or pressing on the side, it still depends on how much water is above that particular slice of glass at a certain depth. So if I instead asked how much fluid force is being exerted on, say, this front side of the aquarium, now it becomes a whole new ballgame because now that piece of glass isn't all at the same depth. So we have to look at a slice of that glass at a constant depth and then find the force on that slice and then integrate to add up all the forces. Let me show you. So we want to find, oh my gosh, I want to move the piece of paper here. So now we're looking at just the front slice of glass or the front piece of glass that's on our aquarium. That is 7 feet wide by 4 feet tall. And the idea is to find the fluid force due to pressure on the front of the tank. Well, we're still using the same idea that the force is just depth times area times density. Depth times area will give you volume. Volume times density will give you force. So we're going to look at a slice or a strip of glass that is, I'm going to say it's y feet high. The bottom is y equals 0. The top is y equals 4. So that slice, the force acting on our slice is going to have, well, going to have area times depth times density. Not too terrible, really. Not as bad as water. So area, no big deal. The area is 7 feet wide by dy feet tall. The depth is 4 minus y feet. And the density, once again, is 62.5 pounds per cubic foot. So then, if that's the force acting on just that strip there, to find the force acting on the entire window pane, we have to add up all the forces from as low as a strip at y equals 0 to as high as a strip at y equals 4. So the total force is going to be the integral from 0 to 4 of all that. 7 times 4 minus y times 62.5 dy. And I don't need to put in the units, right? The units all work out just fine. Feet, pounds per cubic foot. Good to go. So then the rest of this is not too terrible. It's too bad it wasn't 8 feet wide because 8 times 62.5 is great. It's 1,000. It's 500, sorry. 100? Yeah, 500. But it's not 7. So we have 7 times 62.5, which is less nice. Integral from 0 to 4 of 4 minus y. That should be not terrible at all. It's going to be, let's see, the integral of 4 minus y is going to be 4y minus y squared over 2 from 0 to 4. And often when you integrate this kind of thing all the way up, you kind of get like the number squared minus half the number squared. That kind of always happens. It's going to happen here. I'm going to get 4 times 4, 4 squared, minus 4 squared over 2. So I'm going to get 16 minus half of 16. So I'm going to get 7 times 62.5 times 8. And then that's going to be 7 times 500, which is coincidentally, purely coincidentally, is a coincidence, also 3,500 pounds of force. But it is a coincidence. Yeah. Also in the notes as well. Coincidence. It really, so yeah, it's a coincidence. Sure. 6 minutes. Let's not. So it's all about the setup. It's all about drawing the picture, finding a segment or a strip or a slice that is all typically going to move the same amount of distance if you're talking about work, or is at the same depth if you're talking about fluid force, or in the other frame of mind, which I'm not good at, talking about work, it's some length that has a certain force. It's going to move a tiny bit. That's I can't do it that way. It's not how I want to think of it. But drawing that strip that's going to move some distance and then finding how much of the thing you're trying to calculate is happening for that little bit and then adding it all together. That's the general, very broad idea. And I know a lot of the examples are kind of wonky, but the only way to really kind of do this is to practice it. So practice, practice, practice. Yeah. Oh, the tendon sheet. No, I passed that, right? Yeah. Sorry. I thought you were going to say that. Yes.
Same question, like different.
The for the bottom part.
Yeah, why did you draw it like in that like column?
So what I was kind of trying to point out here is for that little square, the pressure on it is the weight of that column of water that's directly above it, but only that's directly above it, not anything off to the side over here. So, but I didn't really do anything with that. So you're right to ask, like, what was that for? It was not really for anything. It was just kind of the idea being that if you have some little kind of region here, like you have a 1 foot by 1 foot area with, say a depth of 5 feet of water above it, then the pressure on that little strip, that little area, is going to be 5 times the density of water. Because it's just the volume, 5 cubic feet, the volume of water multiplied by its density, because that is the weight of water that is above that area. Yeah. All right. You've suffered enough. You're free to go. And please do come see me in office hours if you have questions about this. I'm happy to talk about the work stuff. It just really, it takes thinking about and talking it out with people to like, you should, if there's anything you're going to work with other people on, this should be it. Because you really sometimes need to talk about it with someone else to kind of figure out why you're thinking of it right or why you're thinking of it wrong. So do work with each other, please. It's a good idea. All right, that's all. Thank you. Where'd that other example go? Work is a lot of work.
That midterm was so bad.
Oh yeah.
Yeah, well, at least I don't know.
And what was I forget, what was the content for that midterm? It was all like the integration methods.
It was, but, and then I got stuck on, there was like displacers and washers.
Oh, well,